Hey guys, Reeves here, looking to do review 21. Okay, so 20 kilogram box on a horizontal frictionless surface is moving to the right at a speed of 4 meters per second. Then the box hits and remains attached to one end of the spring, one end of a spring of negligible mass, whose other end is attached to the wall. As a result, the spring compresses to a maximum distance of 0.5 meters and oscillates back and forth. Okay, so the first question. The spring does work on the box from the moment the box first hits the spring to the moment the spring reaches its maximum compression. Indicate whether the work done by the spring is positive or negative. Justify your answer. Okay, so let's give a little bit of a let's do what I like to do, which is make a little bit of a. All right, so here's my mass. Right, here's the spring, right? Let's say this is x is equal to 0. Look at that, here's the spring. It compresses to x is equal to 0.5, right? Oscillates back and forth, and here it is at x is equal to minus 0.5, right? It doesn't really matter, right? So this is 5 this way, this is 5 this way. It oscillates back and forth. So this guy is moving this way, hits the spring, and compresses, right? So it's saying the spring that is pushing on the box, which is moving to the right, does work. Is the work positive or negative? Well, in this particular case, the work is negative. Why is the work negative? Because the force is in the opposite direction of motion, right? The box is moving to the right. The force of the spring, right, is pushing to the left. So for A, right, it does negative work, right? Why? Because the force is in the opposite direction opposite direction of displacement. Let's play that, right? That's a good way to say it. Opposite direction of displacement. Okay, so that's AI. 2, calculate the magnitude of the work done. Okay, so AI, double I, right? All right, so, well, how am I going to do this? I want to know, as it moves to this spot over here, right, how much work is done? Well, what happens on a spring? Well, I should say, what happens with a mass on a spring? As it wiggles back and forth, right? What type of energy do I have here? At x equals 0, I have the maximum kinetic energy. It's going the fastest, right? When it's totally compressed over here, it's got what? Potential, right? Kinetic, potential, zips back, kinetic, potential, there, right? And it goes back and forth, back and forth. So how can I find out how much work, right, is done by the spring? Well, I can use conservation of energy. I can say, right, well, since energy is conserved, K at this point has to be equal to potential energy over here, which, by the way, is going to be equal to the work done on the spring, right? So 1/2 mv squared, that's going to be equal to the potential energy stored in the spring, which is going to be equal to the work done on the spring. So 1/2, I believe this is a 20 kilogram box, and we were going initially at what? 4 meters per second, U, right? So what did I get here? This is going to be 16, right? 20, I did this already, so I get a potential energy of 160 joules. Okay, so that's how much work was done on the spring. B, all right, so B. Calculate the spring constant. Okay, spring constant. Well, since, by the way, I found out what U is, right? Potential energy is 1/2 K x squared. So I know that this is 160 joules, 1/2 K. We have compressed 1/2 meter, square that, do a little bit of math there, and what am I getting? I'm going to get myself 1,280 newtons per meter. Sorry, looking at my notes here. Newton meter. Okay, so that is the spring constant. C. What's C? Okay, calculate the magnitude of the maximum acceleration. All right, so how do I find acceleration? F is equal to ma. All right, well, I know the mass. Can I find the force? Yes, I can. I can find the force by force in the spring is equal to what? Kx. I know that this is 1,280. We just found there. We know that it compressed a half a meter. So I think this was 640 newtons, right? So 640 is equal to what? 20, right? So that's the mass, 20. A, do a little bit of dividing, about 32 meters per second squared, that is, right? So that's C. D. All right, calculate the frequency of oscillation. So what's the frequency of oscillation? Okay, so that is D, right? All right, so frequency. You know what? I'm going to solve it. Well, first of all, I know that period, right, is equal to 1 over the frequency, right? So I'm going to find it indirectly by finding the period. And I know that the period of a spring mass system is 2 pi m over k. So 2 pi, mass 20, found out the spring constant was 1280. Doing a little bit of math here, like I said, I totally did this already, right? Where is it? There it is, right? I'm going to get a period, right, of 0.785 seconds. So period is equal to 1 over the frequency, so 0.785, 1 over the frequency, right? So 1 divided by this, right? We're going to take the reciprocal, and I think I got a frequency of 1.27 hertz, okay? So that is D. All right, next, right? On the axis below, these I'm going to draw on the graphs here, right? Yeah, so E. So now we're looking at E, right? On the point where the box makes contact with the spring, X is directed, so this is positive, this is negative, right? So on the axis below, sketch the kinetic energy of the oscillating box as a function of position from negative X to here. All right, well, first of all, we know that energy, right? By the way, we have kinetic energy, positive and negative. I know that energy can't be negative, right? It's not. It's a scalar, right? So it can't be negative, right? So what do I have? Where is my kinetic energy, the maximum? Well, the kinetic energy is a maximum at my 0 position, right? And what happens at the ends over here, right? So what happens at the ends? The ends, right, the kinetic energy comes to a rest. So these guys are at 0 right here. But the question is, how does this look, right? Well, K is equal to 1/2, right, mv squared, right? So this is squared, so this business has to look like that. Okay, so there is the graph for kinetic energy. Okay, on the axis below us gets the acceleration of the box, right? So acceleration, I'm gonna go over here. So how does my acceleration look? Well, okay, so let's take a look over here, right? So here is my system as it wiggles back and forth. Where is my acceleration the greatest? Well, at here, right, where the acceleration is going to be greatest, where the force is a maximum. And the force is going to be a maximum where the spring is compressed the most, here and here, right? But now the question is the force really accelerations positive or negative? Well, at this particular point, way over here, which way is the force and acceleration pointed, right? So this is a big negative. How about this side over here? That's a big positive, right? So looking at my graph, obviously the acceleration is going to be 0 at this position right here, right? So we're going to get something that looks like that. Okay, so there is the graph of acceleration, right, versus position for this particular graph. Now, I will say, I assigned this problem here as well, but I did this already, right? I unfortunately did it twice. So this is going to be, I solved this already at review number 13, right? So if you need to take a look at that, review 13, all right? See you later.